Okay, lab data analysis. In the last video, I showed you how to plot points, put a fit line on there, and do a curve fit. So the curve fit's a little bit new. So now the question is, how do we take that and say whether or not this person had a constant acceleration? Well, if you took physics 11 honors last year, something we talked a lot about was when you have a curved position versus time graph, x versus t, if x is proportional to t squared, right? If x is proportional to t squared, that's what we called curved, right? Then what we saw was velocity was proportional. Velocity was proportional to t. It was linear, curved. So sorry for the poor handwriting. We had linear. And then that meant the acceleration was constant or flat. So A was constant. All right? Flat. So the format of this function ends up being x equals 1/2 at squared plus v naught t plus x naught. It's a general quadratic form. Now, last year in Physics 11H, we said d, or delta x, equals 1/2 at squared plus v naught t. Well, d, or delta x, is just x minus x naught. It's the change in position. So if we put in d there, and all we would do was move the x naught over to the other side, and you end up with this form. This is the more powerful form of the equation, really. This is your position at any time is equal to 1/2 the acceleration times the time squared plus the initial velocity times time plus the initial position wherever it started. So that's not the way it is on the physics reference table, so that's why we didn't deal with it that way. This function ends up being v equals at plus v naught. And this is simply a equals a naught, right? So y equals mx plus b, and y equals b, so to speak, right? Kind of remember that. So slope of velocity versus time is acceleration. So when we look at these graphs, right, we have a nice quadratic function here. Now, we might have called that a side opening parabola, right, last year, and we might have squared the x to get that figured out. But for this, we did the quadratic curve fit, and it makes it so that when it's curved sideways like that, it just makes this coefficient negative. So we have a negative acceleration here. So that's the general form of these graphs. So this is kind of a little lecture note as well. So if you have a curved, linear, flat, if you start with a linear position versus time, then you have a constant velocity and zero acceleration. So it would be linear, flat, zero. And as we saw in worksheet 0, if we have a curved velocity versus time, we also have a curved position versus time and a linear acceleration versus time. All right? So this applies to the lab in that when we look at the equations, they should relate to one another. So but when we did the curve fit on this position versus time graph, the equation is, I'm going to have to get down and kind of look here. You might see me in the frame. I don't know. It's x equals negative 0. It's basically 40 t squared. I'm not going to put the units on it quite yet. You know what? I'm going to leave space for the units. That would be smart. This is my second take of this video, and that should help. Plus b, which is 3.7 times t. So I'm just putting the numbers that are in the little box. There's no units in there, though. And plus c, which is 0.014. So 2 sig figs on all the coefficients is plenty. The velocity versus time graph here is vx, v equals m, which is negative 0.85 times t. This one has units. It's meters per second as written, which is an acceleration, which it should be, times t plus 3.8 meters per second. So this is great. All right, let's figure out what these units should be on this. Well, all of these terms, we have three terms, right? This term, and this term. All three of these terms have to end up with units of meters. So that one's simple. It's just 0.014 meters. That's our initial position, as we saw a little earlier in this video. The units on this one, this is V naught, turns out, which agrees with this, right? That should be meters per second. Because look, if it's meters per second, and then you multiply it by a time, the seconds are going to cancel, and it's going to give you meters on that term. This term has to be meters per second squared, which is an acceleration, but that's not the acceleration, right? It's about half of the acceleration. It's about half of the acceleration. So that worked out. All right, so those are your, what we call, the equations in black here. These are your experimental equations. This is an experimental equation. All right, that's what we called those in Physics 11H. So when I refer to this experimental equation, it's the ones you actually produced in Logger Pro. Now, the general equations, or the theoretical equations, are what would go on a reference table. All right, so the general equation for this one is position equals 1/2 AT squared plus V initial T plus the initial position. The general equation for this one is V equals AT plus V naught. So 0 there. So those are your general equations. Your experimental equations, your general equations. All right, so I'm going to pause this here. I'm going to move to the computer and talk you through the lab write-up a bit. All right? All right. I'll see you in a second.